You take flour, you take water, you mix them together and nothing happens. Dead paste. But drop in a pinch of yeast and watch what happens over the next 60 minutes. The dough doubles, it breathes, it rises like something alive. And here's the thing nobody tells you. The reason bread rises is way stranger than you imagine. It's not just gas, it's not just yeast eating sugar, it's a war between proteins, a race against death inside every single cell, alcohol vaporizing into invisible fuel, and a creature so tough it can sleep for 4,000 years and wake up hungry. Ancient Egyptians thought it was a miracle. Turns out they were not wrong. If you value documented food science and archaeological history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Frontiers in Genetics, published in October 2020, PMC articles on dormancy mechanisms from 2020, and Science Direct research on fermentation, published April 20 to 24. We're pulling from primary research at the molecular level, not food blogs. Now back to the information. Let's start with what yeast actually is. Saccharomyces cerevisiae. Baker's yeast? A single-celled fungus so small, you need 40,000 of them lined up to span 1 inch. Each cell is alive. Each cell has a nucleus, neural mitochondria, a metabolism. Each cell can reproduce by budding every 90 minutes under ideal conditions. And each cell has one job when you drop it into dough. Eat sugar and excrete waste. That waste is what makes your bread rise. But the waste is not what you think. Here's the equation. 1 molecule of glucose goes into the yeast cell. 2 molecules of carbon dioxide come out. 2 molecules of ethanol come out. Equal parts. For every bubble of carbon dioxide trapped in your dough, there's an equal amount of alcohol sitting in the mixture. The yeast is brewing beer inside your bread. Louis Pasteur proved this in 1857. He was 35 years old, working in Lille, northern France. A local beet sugar producer named Monsieur Bigot was having problems. His fermentation tanks kept souring. Pasteur looked under a microscope and saw yeast cells, living cells. He demonstrated that fermentation was not a chemical process, as Justus von Liebig had claimed. It was biological, life without oxygen. Pasteur published his findings on August 3, 1857, to the Société des Sciences de Lille. The paper appeared November 30th. 1857. He called it life without oxygen. Fermentation is yeast breathing in an airless environment. Before Pasteur, people had been making bread for over 3,000 years without knowing what yeast was. The earliest physical evidence of leavened bread comes from ancient Egypt between 1300 and 1500 BCE. Archaeologist Delwyn Samuel from Cambridge used scanning electron microscopy in 1994 to examine bread loaves from New Kingdom Egypt around 1400 BCE. She found yeast granules preserved in the bread structure, still visible. The yeast had survived desiccation. Egypt had 117 words for bread, 40 words for beer, but not one written recipe. They captured yeast from the air. They kept starters alive by backslopping. Old dough into new dough, old beer into new beer. The yeast traveled from Egypt to Greece to Rome. Professional bakers did not appear in Rome until 168 BCE after a war with King Perseus. Pliny the Elder recorded it. In 2019, a physicist named Seamus Blackley worked with archaeologist Serena Love and microbiologist Richard Bowman to extract yeast from Egyptian ceramic pottery at the Museum of Fine Arts, Boston, and Harvard's Peabody Museum. The pottery dated to around 2000 BCE, 4,000 years old. Bowman developed a method to extract yeast from the pores of the ceramic without damaging the artifacts. They applied liquid yeast food to small areas. The yeast flowed into the liquid. They incubated it. The yeast woke up. Blackley baked bread with it in August 2019. The bread rose. It smelled sweet, rich, and sour, different from modern sourdough. The yeast had been dormant for 4 millennia. How does yeast survive that long without food? Quiescence. When nutrients disappear, yeast cells enter a dormant state. Metabolism drops to near zero. They shut down over 95% of their 6,000 genes. They stop dividing. They build up trehalose and glycogen as energy stores. Their cytoplasm changes from fluid to solid. They can survive in this state for months, years, potentially thousands of years. Research published in Molecular Systems Biology in November 2020 showed that dormant yeast spores gradually lose their gene-expressing ability over time. They measured it. Each dormant spore has a specific probability of germinating that decreases as its RNA polymerase levels drop. When gene expression ability vanishes completely, the spore dies. But before that point, it can wake up, add water, add sugar, add warmth. The yeast comes back, In 2010, divers recovered beer from a shipwreck in the Baltic Sea, and the ship had sunk around 1800. The beer had been sitting on the seafloor for 200 years. They opened the bottles. The yeast was still viable. Barely, but viable. In the same study published in FAMA's Microbiology Reviews in March 2012, researchers noted that around 1800 Donarus, a sailing barge carrying bottled champagne and beer, possibly sent by France's King Louis XVI to the Russian imperial court, sank in the Baltic. The yeast hibernated for 2 centuries. When conditions became favorable again, it could germinate. That's the power of quiescence. Yeast treats time differently than we do. Now back to your bread dough. You mix flour and water. 2 proteins in the flour, gluten and gliadin, come into contact with water and immediately start binding. Gluten molecules link up with each other via disulfide bonds. These are among the largest protein molecules ever identified. They form long, stretchy strands. Gliadin proteins are more compact. They contribute viscosity and flow. Together, they form gluten. Without water, gluten does not exist. The proteins stay separate. Add water and the network begins. Knead the dough and you accelerate the process. Kneading jostles water and protein molecules. More gluten finds more gluten. More gliadin fills the spaces. The network strengthens. Proteases, protein snipping enzymes in the flour, cut gluten strands into smaller pieces that can make additional connections. The dough becomes elastic. It can stretch without breaking. But here's where it gets strange. Gluten does not just trap gas. It moves in response to gas. As carbon dioxide bubbles form from yeast fermentation, they jostle the gluten network. They push water molecules and protein molecules around. This movement causes more gluten chains to form even without kneading. That's why no-knead bread works. The gas bubbles do the work. Researchers at KU Leuven published comprehensive reviews in 2017 showing that yeast fermentation and gluten development happen in parallel. They're linked. The carbon dioxide production from yeast directly contributes to gluten structure by creating physical forces inside the dough. This is not passive. The dough is reorganizing itself in response to the gas. Now add the alcohol. For every glucose molecule the yeast consumes, 2 molecules of ethanol form alongside 2 molecules of carbon dioxide. Equal parts. At room temperature, ethanol is liquid. It dissolves into the water phase of the dough. It does not form bubbles yet, but ethanol has a boiling point of 78.4 degrees Celsius. When the bread enters the oven and the internal temperature rises above 70 degrees, the ethanol starts evaporating. It becomes gas. It expands. This contributes to oven spring. Research from Campton BRI shows that carbon dioxide, ethanol vapor, and water vapor all work in series to maintain bubble pressure during baking. Carbon dioxide boils at minus 56.6 Celsius, so it's already gas. Ethanol evaporates at 78.4 Celsius. Water boils at 100 Celsius. They each take over at different temperature stages. Without ethanol vapor, the bread would not rise as much. The alcohol is not just flavor, it's structural fuel. But most of the ethanol evaporates during baking. Studies from the USDA Nutrient Data Laboratory published in 2003 show that baked dishes retain about 40% of original alcohol after 15 minutes of cooking, 35% after 30 minutes, 25% after 1 hour, and 5% after 2.5 hours. Bread bakes for 30 to 60 minutes, typically at internal temperatures reaching 98 degrees Celsius. Most of the ethanol is gone by the time you slice it. That's why bread does not taste like beer, even though yeast made equal amounts of both gases. Here's another strange fact. The yeast does not die immediately when it hits the oven. It becomes hyperactive. As the dough temperature rises from room temperature to around 40 degrees Celsius, the yeast experiences a burst of frenzied activity. This is called oven spring. The yeast is producing more carbon dioxide faster because heat accelerates its metabolism. But this only lasts a few minutes. Once the internal temperature reaches 60 degrees Celsius, yeast cells begin to die. At around 46 degrees Celsius, yeast enzymes start to denature. By 60 degrees, the yeast is dead. From that point forward, the bread is being shaped by physics and chemistry, not biology. The heat expands the gases. The gluten coagulates. The starch gelatinizes. The structure sets. Starch gelatinization is the other half of the rising story. Wheat flour is 75% starch. Starch granules sit in the dough as tight crystalline structures. They're dormant. But when the dough heats above 60 degrees Celsius, something changes. Water molecules penetrate the amorphous regions of the starch granules first. The granules start to swell. At higher temperatures, water breaks into the crystalline regions. The granules burst. Starch leaches out and forms a thick gel. This process is irreversible. Once gelatinized, Starch cannot return to its original crystalline form. The gelatinization typically starts around 60 degrees and completes around 85 degrees in wheat flour. Research published in Science Direct in October 2004 showed that starch gelatinization follows first-order kinetics during baking with an activation energy of 138 kilojoules per mole. As the starch gel forms, it pulls water away from the gluten. The gluten network, now coagulating from heat, transfers water to the expanding starch. This changes the texture. The dough transforms from soft and stretchy to firm and structured. By the time the internal crumb temperature reaches 98 degrees Celsius, the bread is set. The gluten has coagulated into a semi-rigid matrix. The starch gel has locked into place. The gas bubbles, which were expanding throughout the bake, are now frozen in position. You have crumb structure, you have bread, but there's more happening at the molecular level that nobody talks about. During fermentation, yeast does not just produce carbon dioxide and ethanol, it produces glycerol, succinic acid, and dozens of volatile compounds that contribute to bread flavor. Lactic acid bacteria, if present in sourdough cultures, also produce lactic acid and acetic acid. These organic acids lower the pH of the dough. Lower pH strengthens gluten bonds. It also inhibits certain spoilage bacteria. A review published in PMC in September 2022 on sourdough fermentation showed that over 90 different species of lactic acid bacteria have been isolated from sourdough cultures. These bacteria create exopolysaccharides, antimicrobial compounds, bioactive peptides, and short-chain fatty acids. They're not just making the bread sour, they're making it more digestible. They're breaking down phytic acid. They're producing compounds that slow glycemic response. Here's where it gets even stranger. Some ancient grains like einkorn, emmer, and the spelt have different protein profiles than modern wheat. They contain more albumins and globulins and less glutenin and gliadin. This means less gluten formation. Bread made with ancient grains is denser, more cake-like. Archaeologist Seamus Blackley noted this when baking with ancient yeast and emmer flour. The bread had a different texture. It was sweeter. It was denser. The gluten network was weaker. But it still rose, because the yeast still produced carbon dioxide and the limited gluten network still trapped enough gas to create structure. The Egyptians were not making fluffy sandwich bread. They were making dense, nutritious loaves that could sustain workers building pyramids. Workers at pyramid construction sites received 10 loaves of bread per day and several pints of beer. The bread and beer were made from the same emmer wheat, the same yeast, shared back and forth. Now think about the timeline. The yeast goes into the dough. Within minutes, it starts consuming simple sugars in the flour, glucose, fructose, sucrose, but wheat flour is mostly starch, not simple sugars. The starch is long chains of glucose molecules locked together. The yeast cannot eat starch directly, so the flour contains enzymes, alpha amylase, beta amylase. These enzymes break starch into maltose, a disaccharide made of 2 glucose units. The yeast has to consume maltose, but maltose consumption is slower than glucose consumption. There's a lag time. Research published in PMC in November 2020 on Baker's yeast domestication showed that when yeast encounters glucose, it activates glucose repression. This shuts down the genes needed to consume maltose. The yeast has to finish eating all the glucose before it can switch to maltose. This creates a delay in fermentation. In bread dough, this lag can last minutes to hours depending on flour type and yeast strain. During this lag, the dough sits, the gluten develops, the yeast adapts, then fermentation accelerates. Carbon dioxide production increases. The dough begins to rise. In typical bread recipes, the first rise, called bulk fermentation, takes 1 to 3 hours. During this time, the dough can double or triple in volume. Carbon dioxide accounts for over half the total dough volume by the end of bulk fermentation. But the bubbles are not evenly distributed. They're large and irregular. So bakers punch down the dough, degassing. This breaks large bubbles into smaller ones. It redistributes the gas. It also redistributes temperature and nutrients. The yeast cells, which had been clustering in certain areas, get mixed back into the dough. Then the dough rises again. The second rise, called proofing, takes 30 minutes to 2 hours. This time, the bubbles are smaller and more evenly distributed. The gluten network is stronger. The dough holds its shape better. When it enters the oven, the structure is ready to set. But here's what most people miss. The bubbles in bread dough do not start from yeast fermentation. They start from mixing. When you mix flour and water, you're incorporating air. Tiny air pockets get trapped in the dough. The yeast does not create new bubbles. It inflates existing bubbles. Carbon dioxide from fermentation diffuses into the air pockets. The pockets expand. New gas molecules join old air molecules. This is why mixing technique matters. Insufficient mixing means fewer air pockets. Fewer nucleation sites for gas bubbles. The bread will be denser. Overmixing can break the gluten network. The dough loses its ability to trap gas. The bread will collapse. There's a sweet spot. Enough mixing to develop gluten and incorporate air, not so much that you destroy the structure. Salt plays a strange role here. Salt strengthens gluten bonds. It tightens the dough. Research from PMC published in April 2024 showed that adding salt to gliadins dramatically increases the tensile strength of the gluten network. Salt shortens the distance between gliadin nanoparticles. The effect is more pronounced on gliadin than glutenin. This is why most bread recipes call for 1 to 2% salt by weight of flour. Too little salt and the dough is weak, sticky, hard to shape. Too much salt and the dough becomes stiff, resistant to fermentation. Salt also inhibits yeast slightly by creating osmotic stress. The yeast has to work harder to maintain water balance inside its cells, but this inhibition is mild. At normal bread salt levels, around 1.5%, yeast activity is only slightly reduced. The benefit to gluten structure outweighs the cost to fermentation speed. Now, let's talk about temperature. Yeast metabolism doubles roughly every 10 degrees Celsius increase in temperature. At 5 degrees Celsius, yeast is nearly dormant. At 20 degrees, it's active but slow. At 30 degrees, it's fast. At 40 degrees, it's very fast. But at 46 degrees, enzymes start denaturing. The yeast is on borrowed time. Professional bakers control dough temperature precisely. They want dough at 24 to 28 degrees Celsius during bulk fermentation. This gives predictable fermentation times. Too cold and the dough takes forever to rise. Too warm and it rises too fast, developing less flavor. The yeast produces more alcohol and carbon dioxide when fermentation is slower. The dough has more time to develop complex flavors from secondary metabolites. This is why cold fermentation in a refrigerator overnight often produces better tasting bread than fast warm fermentation. The yeast is still working, just slowly, and during that slow work, it's producing more interesting compounds. Refrigeration also gives bakers control. You can mix dough in the evening, put it in the fridge, and let it ferment for 12 to 18 hours. The next morning, you take it out, shape it, proof it for an hour at room temperature, and bake. The long cold fermentation develops flavor. The yeast produces more organic acids. The enzymes in the flour break down more starch into sugars. The gluten network relaxes slightly, making the dough easier to shape. This technique is common in professional bakeries. It's called retardation. You're retarding the fermentation, slowing it down deliberately. But there's a limit. Yeast can survive in a refrigerator for a few weeks. Eventually, it runs out of food. The cells enter stationary phase. They stop dividing. They become quiescent. If you leave dough in the fridge for a month, the yeast will be weak or dead. The dough will not rise well. There's also the issue of over-fermentation. If dough ferments too long, the gluten network breaks down. Proteases in the flour and from the yeast cut too many gluten strands. The dough becomes soupy. It loses structure. It cannot hold gas. Professional bakers watch for this. They look for dough that has doubled in volume, shows a slightly domed surface, and springs back slowly when pressed with a finger. That's the sweet spot. Fully fermented, but not over-fermented. Now let's get into the oven. You've shaped your dough. You've proofed it. The internal dough temperature is around 25 degrees Celsius. You place it into an oven at 220 degrees Celsius. What happens next is a cascade. The surface of the dough heats up immediately. The interior heats up slowly. The temperature gradient is steep. The outside might reach 100 degrees while the inside is still 40 degrees. The yeast near the surface dies first. The yeast in the center keeps fermenting for a few more minutes, creating that final burst of oven spring. Then it dies too. As the interior temperature crosses 60 degrees Celsius, starch gelatinization begins. Water trapped in the dough is pulled into the starch granules. The granules swell. The dough becomes more viscous. At 70 degrees, the gluten starts to coagulate. The protein chains lock into position. The dough transitions from a viscoelastic material to a solid foam. At 78 degrees, ethanol starts to boil off rapidly. The alcohol vapor expands, pushing the bubbles larger. At 90 degrees, starch gelatinization completes. At 98 degrees, the interior crumb reaches its maximum temperature. Water vapor accounts for much of the gas pressure at this stage. The bread is finished rising. The structure is set. But the crust tells a different story. The surface of the bread dries out first. As water evaporates from the crust, the temperature rises above 100 degrees. At 160 degrees Celsius, Maillard reactions begin. Amino acids react with reducing sugars. This creates melanoidins, brown pigments. This creates hundreds of volatile flavor compounds, aldehydes, ketones, furans, pyrazines. The smell of fresh baked bread is mostly Maillard reaction products. At temperatures above 170 degrees, caramelization begins. Sugars break down into simpler compounds, producing more color and flavor. The crust can reach 200 degrees or higher. Meanwhile, the crumb stays around 98 degrees because it's still wet. This temperature difference is why bread has a crispy crust and soft crumb, two completely different environments in the same loaf. Here's where bread science gets weird. The bubbles in breadcrumb are not filled with carbon dioxide. By the time the bread is baked and cooled, most of the carbon dioxide has diffused out. The bubbles are filled with air, mostly nitrogen and oxygen. During baking, as the bread cools, atmospheric air diffuses back into the bubble structure. The partial pressure of carbon dioxide inside the bubbles drops. Nitrogen and oxygen take its place. By the time you slice the bread, the gas composition inside is close to atmospheric air. The carbon dioxide that made the bubbles is gone. It served its purpose and left. This is also why bread stales. Over time, the starch in bread undergoes retrogradation. The gelatinized starch molecules rearrange into a more crystalline structure. They expel water. The crumb becomes firmer. This process is temperature dependent. Bread stales fastest at refrigerator temperatures, around 4 degrees Celsius. It stales slowest at freezer temperatures, below -18 degrees Celsius, and at room temperature. The starch molecules have specific thermal energy levels where retrogradation happens fastest. Refrigeration is the worst place to store bread, room temperature or freezer, not in between. Now let's talk about wild yeast. Commercial baker's yeast, Saccharomyces cerevisiae, is a domesticated strain. It has been bred for specific traits: fast fermentation, strong maltose consumption, good gas production, but wild yeast is everywhere, on fruit skins, on grain husks. In the air, different strains, different species. When you make a sourdough starter from scratch, you're capturing wild yeast and wild bacteria from your environment. You mix flour and water, leave it out, and wait. Within days, the mixture starts bubbling. Wild yeast and lactic acid bacteria have colonized it. They're eating the sugars in the flour. They're producing carbon dioxide and organic acids. Each sourdough starter is unique. The microbial population depends on your local environment, your flour, your water, your temperature. Research published in Frontiers in Genetics in October 2020 showed that Saccharomyces cerevisiae originated in China and spread westward along what would become the Silk Road around 16,000 to 14,000 years ago. The yeast diverged into different populations: beer yeast, wine yeast, bread yeast. Each adapted to specific fermentation conditions. Bread yeast had to become good at consuming maltose, tolerating high osmotic stress from salt and sugar, surviving freezing and drying, and producing flavor compounds. These traits did not exist in the original wild yeast. They evolved through human selection. Bakers kept the yeast that worked best. That yeast reproduced. Over thousands of years, baker's yeast became a distinct genetic lineage. Modern commercial yeast is even more specialized. It's grown in massive fermentation tanks on molasses. The yeast is harvested, washed, concentrated, and sold as compressed yeast cakes or dried granules. Active dry yeast is yeast that has been dried at low temperatures to remove moisture while keeping the cells alive. Instant yeast is dried faster and in smaller granules, so it rehydrates quickly. Both are alive. Both can ferment dough. The difference is rehydration speed and cell count. Instant yeast has more viable cells per gram. It's more potent, but here's the strange part. Even dead yeast contributes to bread. Yeast cells contain enzymes, amino acids, vitamins, glutathione. When yeast cells die during baking, these compounds are released into the dough. Some of them affect gluten structure. Glutathione, a tripeptide, can weaken gluten by breaking disulfide bonds. This is why some bread recipes use dough improvers that contain extra enzymes or reducing agents to counteract glutathione. The dead yeast is not inert. It's chemically active even after the cells die. Let's go back to the Egyptians for a moment. They did not have thermometers. They did not have precise measurements. They did not know what yeast was, but they knew how to make bread rise. They understood fermentation empirically. They kept starters. They knew warm temperatures helped. They knew kneading helped. They knew salt helped. They had accumulated thousands of years of practical knowledge without understanding the underlying mechanisms. When archaeologists tried to recreate ancient Egyptian bread in the 21st century, they found it challenging. The techniques were different. The grains were different. The yeast was different. But the fundamentals were the same. Yeast, water, flour, time, heat. That's all you need. Here's a strange archaeological detail. In 2019, when Seamus Blackley baked bread using yeast extracted from Egyptian pottery, he scored the top of the loaf with hieroglyph X1, the symbol for loaf of bread. It's a half circle. It represents the sound T in hieroglyphics. This symbol appears thousands of times in Egyptian texts. Every time they wrote about bread, which was constantly, they used this glyph. Bread was so central to Egyptian life that it became part of their written language. When Blackley baked his loaf and scored that symbol on top, he was closing a loop that had been open for 4,000 years. The yeast had been asleep in pottery. Now it was alive in bread, marked with the same symbol the Egyptians used. When that bread cooled and Blackley tasted it, he described it as incredibly exciting, rich, sweet, light and airy for an ancient grain loaf. The aroma was different from modern sourdough. It was new. He was tasting something that had not existed for millennia. The yeast was expressing genes that modern commercial yeast has lost. It was producing metabolites that modern fermentation does not produce. The bread was a window into the past, not a reconstruction, not a replica. The actual genetic lineage woken up and put to work. Now let's look at the numbers that matter. A single gram of active dry yeast contains about 20 billion cells. 20 billion. That's almost 3 times the human population of Earth in 1 gram of dried yeast. When you add that gram to 500 grams of flour and 300 milliliters of water, you're inoculating the dough with 20 billion living organisms. Each one starts eating sugar. Each one starts producing carbon dioxide and ethanol. Over 2 hours of fermentation at 30 degrees Celsius, that population can double once or twice. Now you have 40 to 80 billion yeast cells in your dough. That's a lot of metabolism. That's a lot of gas. The yeast produces about 0.9 grams of carbon dioxide per gram of sugar consumed. If your dough contains 10 grams of sugars available for fermentation, the yeast will produce about 9 grams of carbon dioxide. Carbon dioxide has a density of 1.98 grams per liter at room temperature. So 9 grams of carbon dioxide is about 4.5 liters of gas, but the gas is not free. It's trapped in bubbles under pressure. The actual volume increase in the dough is less than 4.5 liters. It depends on bubble size, gluten strength, dough temperature. Typically, dough doubles in volume during bulk fermentation. A half liter of dough becomes 1 liter. The gas produced accounts for that volume increase plus the gas that escapes from the surface. During baking, the volume increases again. Oven spring can add another 20 to 50% volume. This comes from multiple sources. The final burst of yeast fermentation as temperature rises. The expansion of existing gas as temperature rises. The evaporation of ethanol. The evaporation of water into steam. All 4 gases contribute. Research from combining local pressure and temperature measurements during bread baking, published in Science Direct in October 2009, showed that at temperatures lower than 73 degrees Celsius, water vapor contributes about half as much pressure as carbon dioxide. At temperatures higher than 95 degrees Celsius, water vapor contributes at least twice as much pressure as carbon dioxide. The dominant gas changes during the bake. Carbon dioxide rules early. Water vapor rules late. Here's another strange fact. Bread dough is a foam. A semi-solid foam. It's a continuous network of gluten and starch with discrete gas bubbles dispersed throughout. The bubbles are not connected. They're individual pockets. This is different from beer foam or shaving cream where the bubbles can coalesce and merge. Bread dough bubbles are separated by gluten films. If a bubble wall ruptures, the gas moves into an adjacent bubble or escapes to the surface, but the structure of separated bubbles remains. This is why breadcrumb has that specific texture. Each air pocket is surrounded by a solid wall of gelatinized starch and coagulated gluten. The size distribution of bubbles matters. Bread with many small bubbles has a fine crumb. Bread with fewer large bubbles has an open crumb. The size distribution depends on mixing, gluten strength, fermentation time, and shaping technique. Artisan breads often have irregular open crumbs with large holes. This comes from minimal degassing, high hydration, and long fermentation. Sandwich bread has uniform fine crumbs. This comes from thorough degassing, moderate hydration, and controlled fermentation. Same ingredients, different techniques, different bubble structures, but all of it, every bit of it, depends on that initial moment when yeast meets sugar. Without that, you have flatbread, dense, unleavened. The yeast is the switch. It turns flour paste into bread, and the yeast itself is almost absurdly tough. It can survive without food for months. It can survive drying. It can survive freezing. It can wake up after 4,000 years. It can double its population every 90 minutes. It can eat dozens of different sugars. It can tolerate alcohol concentrations that would kill most microorganisms. It can function in low oxygen environments. It can survive high osmotic stress from salt and sugar. Baker's yeast is a survival machine optimized over millennia of coevolution with humans, and we've only used it for bread for a tiny fraction of human history. Homo sapiens has existed for about 300,000 years. Agriculture began about 12,000 years ago. Leavened bread appears around 3,500 years ago in Egypt. That's 1% of human existence. For 99% of our species, history, we did not have bread that rises. Now we take it for granted. You buy yeast in a packet. You mix it into flour. You wait. The yeast does its work. 2 hours later, you have dough. 40 minutes in the oven, and you have bread. The process is so routine, we forget how strange it is. We forget we're farming microscopic fungi. We forget we're harnessing their metabolism to reshape gluten and starch into an edible foam. We forget we're vaporizing alcohol to inflate bubbles. We forget we're orchestrating a complex series of biochemical and physical transformations that depend on precise timing and temperature control. Ancient bakers did not forget. They knew bread rising was magic. They worshipped deities of grain and fermentation. They believed invisible spirits made the dough come alive. They were not entirely wrong. The spirits were real. They were yeast cells. Single-celled organisms with their own DNA, their own metabolism, their own evolutionary history. Organisms that have been traveling with humans for thousands of years, domesticated like dogs and wheat, shaped by our needs, shaping our diets in return. When you bite into a slice of bread, you're eating the fossil record of that relationship. The gluten network shaped by kneading, the starch gel set by heat, the bubbles inflated by yeast fermentation, the flavor compounds produced by yeast metabolism and Maillard reactions. Every component has a history. Every component required discovery, refinement, optimization. The bread in your hand is not simple. It's the endpoint of 3,000 years of accumulated knowledge about how to manipulate yeast, gluten, and starch into something delicious. And here's the final strange twist. We still do not fully understand it. Researchers are still publishing papers on gluten structure, starch gelatinization, yeast metabolism, bubble dynamics. We can make bread, we can make great bread, but the complete mechanistic picture at the molecular level is still being worked out. How exactly do glutenin and gliadin molecules organize into a network? What determines bubble size distribution? Why do some yeasts produce more flavor compounds than others? How does hydration percentage affect gluten cross-linking? These are active research questions in food science. In November 2024, a team at the Museum of Fine Arts Boston and the Peabody Museum at Harvard confirmed through genome sequencing that the yeast they extracted from ancient pottery was distinct from modern commercial strains. It had genetic variations that have been lost in industrial yeast production. This ancient yeast was making bread differently at the molecular level, different enzyme expression patterns, different metabolite profiles, different fermentation kinetics. It was not just old yeast. It was a different lineage, and it still worked. After 4,000 years of dormancy, it could still make bread rise. That's what makes bread rising so strange. It's not just chemistry, it's not just physics, it's biology, living cells doing what they evolved to do, eating sugar, excreting waste, reproducing. And humans figured out how to harness that process to transform inedible grain into the foundation of civilization. Every loaf is a miniature fermentation tank. Every slice contains millions of bubble fossils where yeast once lived. The reason bread rises is not just gas, it's life. It's a controlled biological process that we've been perfecting for 3 millennia, and we're still learning new things about it. In 2024, researchers at Science Direct published findings showing that during bread making, the protein composition of gluten changes dramatically from mixing to baking. Alpha and beta gliadins decrease. Glutenin subunit content increases. Gluten macromolecular polymers increase. Free sulfhydryl content decreases upon baking, indicating structural changes in the gluten network. As baking progresses, the role of hydrogen bonds and hydrophobic interactions diminishes, while intermolecular beta sheet content increases due to protein aggregation. The gluten is reorganizing itself at the molecular level throughout the entire baking process. It's not static, it's dynamic. The proteins are moving, bonding, breaking, rebonding in response to temperature and moisture changes. The final bread structure is the frozen endpoint of that dynamic process. So when someone asks why bread rises, the real answer is complicated. Yeast eats sugar and produces carbon dioxide and ethanol in equal amounts. The carbon dioxide inflates pre-existing air bubbles trapped during mixing. The gluten network, formed from glutenin and gliadin proteins, cross-linked by disulfide bonds and strengthened by salt, traps the gas bubbles. The ethanol evaporates during baking, adding to bubble expansion. Starch gelatinizes at 60 degrees, absorbing water and forming a gel that stabilizes the structure. Gluten coagulates at 70 degrees, locking the protein matrix into place. Water vapor pressure maintains bubble structure as the bread cools. The yeast dies at 60 degrees, but its metabolic waste products remain, shaping flavor and texture. The final cooled bread is a solid foam with bubbles filled with atmospheric air. surrounded by gelatinized starch and coagulated gluten. That's why bread rises. It's microbiology, it's protein chemistry, it's starch physics, it's thermodynamics, it's gas laws. It's all of it happening simultaneously in a complex orchestrated sequence that humans figured out by trial and error over thousands of years. We did not understand the mechanisms. We did not need to. We just needed to know that if you mix flour, water, yeast, and salt, then wait. Then apply heat, you get bread. The yeast would do the rest. And the yeast is still doing the rest, right now, in bakeries around the world, in home kitchens, in research labs, Saccharomyces cerevisiae eating maltose, producing carbon dioxide, producing ethanol, inflating dough, making bread rise. The same organism that the Egyptians used 4,000 years ago, the same process that Louis Pasteur explained in 1857, the same chemistry that modern researchers are still studying in 2024. The reason bread rises is ancient, fundamental, biological, and much stranger than you imagined.